Hello. Today's lecture will cover some basic notions from the analysis of algorithms and the repeated square and multiply algorithm for modular exponentiation. I'll motivate the topic of algorithmic number theory by recalling the fundamental theorem of arithmetic. Every integer n, at least 2, has a prime factorization, and this factorization is unique up to ordering of the prime factors. You've actually known this theorem forever. Since you knew how to factor, you knew that if you factored the number 15, you always got the same answer, namely 3 times 5 or 5 times 3. An interesting question that arises from this theorem is the following. Given a number n, well, you know that its prime factorization exists, but how do you actually find it efficiently? Of course, you can always find the prime factorization of n by trial division. So you trial divide n by the prime numbers 2, 3, 5, 7, 11, and so on, up to the square root of n. And by then, you will have found all the prime factors of n. This algorithm clearly isn't fast. So the interesting question is, can we find the prime factorization of n efficiently? A related question is the following. How do we efficiently verify an alleged prime factorization of n? So, suppose that you give me a number n, and I give you back its prime factorization. How do you efficiently determine whether I gave you the correct prime factorization? Of course, you can multiply the factors together to see if they give you n. But the crux of the question is, how do you test whether each of the factors I gave you is indeed prime? So we have a second interesting question. Given an integer n at least 2, how do we efficiently decide whether n is prime or composite? It turns out we don't know the answer to the first question. We do know factoring methods that are significantly faster than trial division, but these methods are not efficient. In fact, we don't even know whether such an efficient method exists. On the other hand, the second question has been fully settled. So we know efficient methods for deciding whether a number n is prime or composite. These two answers are very useful in the RSA public key encryption scheme. In RSA, any entity can efficiently select two large prime numbers p and q and compute their product n, whereas anyone else who learns n cannot efficiently determine the prime factors p and q. I should also mention that these two questions are actually mathematically precise questions. One can make the questions rigorous by defining efficient to mean a polynomial-time algorithm on a Turing machine. I'll next make the notion of efficiency a bit more precise. These are notions you would typically see in a computer science class in algorithms. An algorithm is a well-defined computational procedure, more precisely a Turing machine, or less precisely, a computer program written in your favorite programming language that takes a variable input and eventually halts with some output. For example, an algorithm for integer factorization takes as input a positive integer n and outputs the prime factorization of n. The efficiency of an algorithm is measured by the scarce resources it consumes. Usually, we measure time, but sometimes we also measure space, the number of processors, the number of chosen plaintext ciphertext pairs, and so on. In today's lecture, the measure of efficiency will be time. Now, in general, one can expect that the bigger the input to the algorithm, the longer the algorithm will take. And so, we should measure the efficiency of an algorithm in terms of how large the input is. More precisely, I'll say that the input size is the number of bits required to write down the input using a reasonable encoding. For instance, the size of a positive integer n in ordinary binary encoding is log base 2 of n plus 1 bits. Note that if k is log base 2 of n, then n equals 2 to the power k. So there is a big difference between n and k. Don't mix up the input and the input size. The running time of an algorithm is an upper bound as a function of the input size of the worst-case number of basic steps that the algorithm takes over all inputs of a fixed size. I'm now ready to present the formal notion of efficiency. We'll say that an algorithm is a polynomial-time algorithm if its running time, or perhaps the expected running time for randomized algorithms, is of the form big O of k to the c, where c is a fixed constant and k is the input size. I'll recall the big O notation for you. Recall that if f and g are functions from the positive integers to the positive real numbers, then f is big O of g means that there exists a positive constant c and a positive integer n0, such that f of n is at most c times g of n for all n at least n0. In other words, the function values f of n are upper bounded by a constant times the function values g of n for all sufficiently large n. For example, the polynomial on the left is big O of n cubed because as n gets large, the dominant term is 7.5 times n cubed, and the big O notation suppresses the constant 7.5. Back to the definition. An algorithm is polynomial-time or efficient if its running time grows only modestly as the input size grows. Let's look at some polynomial-time algorithms for basic integer operations. You saw some of these algorithms in grade school when you studied addition, subtraction, multiplication, and division. The input to these algorithms are two k-bit positive numbers a and b. So a and b are each roughly 2 to the power k. K is their size, so the input size is 2k, or big O of k bits. Let me convince you that the algorithms you learned in grade school for adding, subtracting, multiplying, and dividing integers are polynomial-time algorithms. Addition and subtraction have linear running times, whereas multiplication and division have quadratic running times. As it turns out, the Euclidean algorithm for computing the greatest common divisor of a and b is also a polynomial-time algorithm. Let's first look at integer addition. I'm adding here two numbers a and b, each at most k bits long. I'll add the bits of a and b from right to left. So I first add 1 plus 0 to get 1. Then I add 1 plus 1 to get 2, which in binary is 0 with the carry bit of 1. Next I add 1 plus 1 plus the carry bit 1, giving 3, which in binary is 1 with the carry bit of 1, and so on. So for each pair of bits in a and b, I'm adding 2 bits plus a carry bit. If I define the bit operation to be either adding 2 bits with the carry bit, or reading a bit, or writing a bit, then the running time of this algorithm is big O of k bit operations. This is an upper bound, but it's also a lower bound because any algorithm for integer addition must use at least k bit operations, namely, the algorithm must read the bits of the input. So I could write the running time more precisely as big theta of k bit operations. But I'll be informal and use the upper bound of big O of k bit operations. You can check that subtraction can be done in big O of k bit operations. Let's multiply two k-bit numbers a and b using the schoolbook method. If the rightmost bit of b is 1, then I write down a copy of a. I then look at the second rightmost bit of b, And if this bit is a 1, then I write down A shifted 1 bit to the left. I continue writing down copies of A, shifted some bits to the left. For each bit of B, that's a 1. And then I add these numbers together. There are at most k such numbers, and each is at most 2k bits in length. Hence, there are at most k-1 additions of numbers that have bit length at most 2k. So the additions take big O of k squared bit operations.
I'll mention, as an aside, that one can do better. In 2020, it was proven that k-bit numbers can be multiplied in big O of k log k bit operations. This algorithm is extremely complicated and highly inefficient in practice because of the very large constants that are suppressed by the big O notation. An outstanding open question is whether k-bit numbers can be multiplied in big O of k bit operations. In this sense, integer multiplication is not fully understood.
I'll let you verify that ordinary long division of two k-bit integers can be done in big O of k squared bit operations. Lastly, I'll take a look at the Euclidean algorithm for computing the greatest common divisor of two k-bit numbers a and b. In Euclid's algorithm, you begin by dividing a by b, obtaining a quotient q1 and a remainder r1. If the remainder r1 is non-zero, then you divide the previous divisor b by the previous remainder r1 to get a new quotient q2 and a new remainder r2. You continue dividing the previous divisor by the previous remainder to get a new quotient and a new remainder until you get a zero remainder. Then the GCD of a and b is the last non-zero remainder that was encountered. Euclid's algorithm terminates because the remainders are a strictly decreasing sequence of non-negative integers and so must eventually reach zero. In fact, one can prove that the total number of divisions is at most 2 times k. And so, since the numbers get smaller and each division takes big O of k squared bit operations, the total running time of Euclid's algorithm is big O of k cubed bit operations. In fact, a better upper bound on the running time of Euclid's algorithm is big O of k squared bit operations. The big O of k cubed upper bound is correct, but big O of k squared is a better upper bound on the running time of Euclid's algorithm.
The natural method for computing greatest common divisors is to find the prime factorizations of a and b and then multiply together the common prime factors. However, this method is not efficient, since no polynomial-time method is known for integer factorization. So, it's really quite remarkable that Euclid's algorithm can find the greatest common divisor of a and b in the same running time as a single long division. And Euclid's algorithm is more than 2,000 years old.
Let's now take a look at basic modular operations. The input to these operations is a k-bit modulus n, and integers a, b, and m between 0 and n-1. Since n is k bits long, a, b, and m are also each at most k bits in length. And so the input size is at most 4k bits, or big O of k bits. We'll examine the basic algorithms for addition modulo n, subtraction modulo n, multiplication modulo n, inversion modulo n, and exponentiation modulo n. We can add a and b modulo n by adding a and b as integers and then subtracting n once if necessary. Since addition and subtraction both take big O of k bit operations, the running time of this algorithm is also big O of k. Similarly, we can compute a minus b modulo n by first computing the integer a minus b, and then adding n once if necessary, This takes big O of k bit operations. We can multiply a and b modulo n by first multiplying a and b as integers in big O of k squared bit operations. The resulting product, which has bit length at most 2k, is then divided by n, and the remainder of the division is a times b modulo n. The division can also be done in big O of k squared bit operations. So the total running time for this operation is big O of k squared bit operations. Let me remind you that x equals a inverse modulo n means that a times x is congruent to 1 modulo n, and x is between 1 and n minus 1. Also, a inverse mod n exists if and only if the greatest common divisor of a and n equals 1. The inverse of a modulo n can be efficiently computed using the extended Euclidean algorithm. This algorithm for computing modular inverses takes big O of k squared bit operations because that's the running time of the extended Euclidean algorithm. Lastly, a very important operation for public key cryptography is modular exponentation. The operation computes the remainder upon dividing the integer a to the power m by a modulus n. As it turns out, we can do this in polynomial time. The algorithm is fairly straightforward, but far from obvious. Let's first look at a naive algorithm for performing modular exponentiation. So to compute a to the power m modulo n, we'll first compute a to the power m by repeatedly multiplying a by itself, and then divide the resulting number d by n to get its remainder. This algorithm is terrible. More precisely, it's not polynomial time. The bit length of the number d is roughly log base 2 of d, which equals log base 2 of a to the m, which is m times log base 2 of a. Now log base 2 of a is big O of k, since a has bit length at most k. And m is big O of 2 to the k, because m has bit length roughly k. So the bit length of d is big O of 2 to the k times k, which is not polynomial in k. Therefore, just writing down the gigantic number d is inefficient. And so the running time of the algorithm, in the worst case, is not polynomial in k. So this is not a polynomial time algorithm, which agrees with our intuition that the algorithm is not efficient. Here's a second naive algorithm, which at least ensures that the numbers involved don't get too large. We'll initialize a to little a, and then repeatedly multiply a by itself modulo n. So for each multiplication, we divide the result of the product by n and take its remainder. This ensures that a never gets too large. Finally, we'll output a as a to the m modulo n. This algorithm is also not polynomial time. I'll let you verify this as an exercise, but your intuition should tell you that this algorithm cannot be considered to be efficient because we're doing the modular exponentiation by doing the multiplications one at a time. This will be rather slow when the exponent m is large. I'll next show you a much faster algorithm for modular exponentiation. This algorithm is polynomial time. It's efficient in theory and also in practice. Let the binary representation of the exponent m be given by this expression. The mi are the bits in the binary representation, so each mi is 0 or 1. Then, a to the power m can be written like this. And I can rewrite this exponential as this product. Note that if mi equals 0, then the term in the product is 1, and so does not contribute to the product. Hence, I can rewrite the product as a product of the terms a to the power 2 to the I modulo n as I ranges from 0 to k minus 1, and where mi equals 1. This expression then suggests the following repeated square and multiply algorithm for computing a to the m modulo n. In a nutshell, the algorithm repeatedly squares a modulo n, and then multiplies together the terms for which mi equals 1. We begin by writing m in binary. We initialize an accumulator b to be a if the least significant bit of m is 1, otherwise b is initialized to 1. We initialize a to the base a. Then, from I from 1 to k minus 1, we square a modulo n to get the new a, and then multiply a into the accumulator modulo n, provided that mi equals 1. Finally, we return b as the value of a to the power m modulo n. In each of the k minus 1 iterations of the main loop, we perform a modular squaring and perhaps a modular multiplication. And so the running time of the algorithm is at most k modular squarings and at most k modular multiplications, or a total of at most 2k modular multiplications. Since modular multiplication can be done in k-squared bit operations, the total running time is big O of k-cubed bit operations. So this is a polynomial-time algorithm. Here's an example showing the steps of the repeated square and multiply algorithm. In summary, we have polynomial-time algorithms for the basic integer operations and the basic modular operations.
Let me show you some examples next, to convince you that the polynomial-time algorithms for integer arithmetic and modular arithmetic are also efficient in practice and not just in theory. These examples are executed using Maple, a symbolic algebra package. Here's a large integer a, and here is another large integer b. Maple can compute their sum very quickly, and also their difference, and their product. Let's find the GCD of a and b. One way to compute greatest common divisors is to first find the prime factorizations of a and b, and then multiply the common prime factors. Let's factor a first. Well, this number is too big for Maple to factor. And so is b. The problem is that no polynomial-time algorithm is known for integer factorization. Instead, let's use the Euclidean algorithm. We get the GCD almost instantaneously, and this is because the Euclidean algorithm is a polynomial-time algorithm. To check the answer, we will use the extended Euclidean algorithm to find integers x and y, such that ax plus by equals the GCD of a and b. So here's x, and here is y. Finally, we'll check that ax plus by equals the GCD, which it does. Let's next define a modulus n for mod n operations. Maple can quickly compute a plus b modulo n, their difference modulo n, and their product modulo n. Let's define an exponent m, and then compute a to the power m modulo n. Maple gives up because it is using the naive algorithm that computes the integer a to the power m first, and the integer a to the power m is too large for Maple. In fact, the number of decimal digits in a to the power m is about 10 to the power 144. In comparison, the number of atoms in the observable universe is only 10 to the power 80. So you can understand why Maple can't even store the number a to the power m, let alone compute it. So we'll use the ampersand symbol, which instructs Maple to use the repeated square and multiply algorithm. And Maple gives us the answer almost instantaneously. This is not surprising, since repeated square and multiply is a polynomial-time algorithm. Having studied the important concepts in public key cryptography, we are now ready to explore the two most widely used families of public key cryptosystems, RSA and elliptic curve cryptography. We'll begin with RSA in Chapter 7, which is comprised of 5 video lectures. I hope to see you in V7a.